Welcome everyone. Let's continue on with the properties of liquids. And here I want to look at a couple of topics. They're short topics. First, we're revisiting the idea of boiling point. Um, Boiling points, of course, we've now looked and defined. It depends on what your external pressure is. And of course, perhaps we need to revisit what the idea here is. So if you think of, say, a beaker, and your beaker is open to the atmosphere. Remember that atmosphere is exerting a pressure, right? That on that beaker of water, the atmosphere presses down on the surface, and you need to add enough energy, or meaning the temperature eventually needs to give enough energy to that liquid so that the vapor pressure will equal. So the vapor will equal the atmospheric pressure, and then only will your liquid be able to escape from the liquid phase into the gas phase. Right, so that's maybe a better way or a clearer way to think of it. So, because there's this pressing down from the atmosphere on your liquid needs to overcome that pressure. And the only way for it to overcome that pressure, the pressure of the vapor itself needs to at least equal that atmospheric pressure. Okay? Right. So it's the vapor pressure is pushing back the atmosphere. And in other words, it needs to be at least atmospheric pressure for it to escape from the liquid phase. All right. And that's why the boiling point is, well, meaning the boiling point of a liquid is the temperature at which the vapor pressure is equal to the external pressure. All right. So sometimes it's confusing to think of it as only atmospheric pressure because why? The atmospheric pressure varies from place to place. So think of it as the vapor pressure must always be equal to whatever the external pressure is that's being applied to your system. So if the external pressure is 20 millimeter mercury, then your liquid will boil at whatever temperature is 20 the vapor pressure will be 20 millimeter mercury. Okay. And then as we said, if the external pressure is 70 millimeter mercury, which is then 1 atmosphere, we define that temperature as the normal boiling point. Okay. So then the normal boiling point of something like water is 100 degrees Celsius. But that's also why at higher altitudes, so like if you go to Mount Everest or if you're here in Gauteng versus at sea level, then your water boils at lower temperatures because we're slightly elevated. So at sea level, you're at exactly 1 atmosphere. But here you're at like 0.95 atmosphere. So meaning the lower your pressure or the further away you get from atmospheric pressure, the less energy or the less pressure your liquid needs to overcome to go into the gaseous phase. And hence, that's why your boiling point varies depending on the external pressure that is applied. Okay, so that's concept. So our first concept that we're looking at. The next concept is what we call critical temperature and pressure. And it comes about if you look at, so I just need to pick the diagram. So remember these vapor pressure curves. So what you had pressure versus temperature. And in principle, you might have thought that, well, that line just continues on forever. But in actuality, it does not. It, at some stage, breaks off into something that looks like that. And it reaches a little point, which we call the critical point. So this is where this diagram or graph comes in. We call that the critical point. And the combination of pressure and temperature we call the critical pressure and the critical temperature at which that happens. And there's some special properties that a compound has once you've reached those points. So meaning it has its normal properties. So you have your liquid, you have your gas, you have your liquid gas equilibrium. And once you've reached those pressure and temperature points, then some interesting things start to happen. And what is that? So meaning we define something called the critical point. So that is the temperature and the pressure at which that happens. And under these conditions, you get something called a supercritical fluid. Now, what on earth is that? Well, that is something that kind of behaves like a gas and a liquid. And the reason is it has the density that resembles that of a liquid, while it has the viscosity, or actually it is, while it has the viscosity of a gas. All right. So, um, meaning it, like I said, it has the properties of both a liquid and a gas. So if you have the viscosity of a gas, so meaning it flows as nice as what a gas does, but it has the density of a liquid, you can in principle do some very interesting things. You can solivate or dissolve substances, but you can as easily make something flow as what a gas can flow. Remember, liquids sometimes flow more difficultly than what gases do. More difficult. Yeah, probably difficultly is not a word. Okay, so a good example of some of this is like CO2. Also, before I get to that, just to give you an idea um, of some other things. For example, for water and most other substances, the critical pressure is 217.7 atmosphere, and the critical temperature is 374 degrees Celsius. So you can see it's a very high temperature and pressure. So not easily attainable. But there are some exceptional cases, and one of those cases where um, it is a notable exception, like I say here, is for CO2. And what makes it very cool as a supercritical fluid is it's very useful as a solvent. So remember, it has the properties of a liquid and a gas. So CO2 is then widely available. It's non-toxic, non-flammable, inexpensive, easy to reach its temperatures because it reaches um, critical its critical constants at 31 degrees Celsius and a relatively low pressure compared to, for example, what water had, right? That's quite intense to reach. And if you were to inspect it, you can see here how it, if you were to increase, you can eventually see, you cannot see the distinction between the liquid and the gas anymore. It just becomes one holistic substance here. Becomes very homogeneous supercritical phase. That's what they call it. The homogeneous phase is supercritical CO2. And what's nice about a supercritical phase is that they can use it in all sorts of things. For example, they use it to extract caffeine from coffee beans um, and all sorts of things. And it's quite useful because if you have a supercritical fluid like this, you don't have a solvent. Because most of the time when you use a solvent, then you have the issue of you need to remove the solvent once your reaction is finished. But with this, we do the reaction here in this phase, so meaning the supercritical phase, and then once you're done, remember it's a gas at room temperature or room conditions, room temperature conditions, STP conditions. So you don't really have to remove a liquid. You can just let it evaporate and then you have your product, whatever you're looking for. So it makes it greener, it makes it more efficient, um, and so it opens up a whole host of cleaner, greener, more efficient synthetic routes. So it's also used for like extracting essential oils, adding hops to beer, um, and other valuable things. So maybe the hops to beer was the more important one that you would be interested in. So cool. That's supercritical fluids. Maybe just more interesting fact than anything else. But now you have that as well.